Yeah, I'm ready. Can you hear me?
Hey, Jeff, we can hear you. Yeah. Go ahead and share your slides and then go ahead and get started when you're ready.
Cool. All right. All right. Are you able to see my screen?
Yep. We can see it, Jeff. Good.
Cool. And I have until 12 for your time, or what's my cutoff?
Uh, yeah, wouldn't mind. Try to stay mostly on schedule, but
Sounds good. I will
not
try
too
to then.
strict.
Well, sorry I couldn't be there in person, but I'm glad to have received the invite and have the opportunity to join remotely. So what we're going to talk about today is a bit of like Mars helicopters and a bit of like a white paper kind of like approach that Seth, myself, and others are trying to put together for like how we could leverage the autonomy that we've flown on Mars for 3 years to basically put the next step for the measurements that are interesting for you in the cryosphere. I'm just going to start by saying I'm not a cryosphere scientist. My background is vision-based navigation and space system engineering. I'm extremely excited to be able to work with that community. But yeah, this is not my background. So hopefully what I'm saying is going to be clear, and I'll do my best to answer your questions. So my talk is divided in two parts. The first one is like passing the message that we had a helicopter on Mars for 3 years. That was my the first mission I got to be part of in space. Also happens to be a very cold world, so I think that's going to be of interest to you. And beyond the story of it, I want to particularly highlight what are the technologies that made that possible. And then we're going to go into like how these technologies could be applied to cryosphere exploration on Earth. And like at least a few of us believe that there's a lot of interesting low-hanging fruits that we're trying to get funded right now. So let's first start with the cool stuff. So we had a helicopter on Mars for 3 years. That was cool. That was part of the Mars 2020 mission, which is still on Mars. That's the Perseverance rover. It's about a vehicle as big as an SUV, for which the primary goal is to find if there was life, basically in the ancient past of Mars. We have a rover also looking for signs of life right now. It hasn't found it, so now we're focused on a dry riverbed in which we believe there was water 100 million years ago. And as part of this mission, there was a small technology demonstration with a quad rotor, with a coax rotorcraft, sorry, which was supposed to try the first powered airborne flight on another planet. So that was objective number one. Just do one flight and show that it's possible. Objective number two was collect engineering data if we wanted to do future helicopters for science mission. That's what we do at JPL. And the overall goal was to have a 1 month, 30-day initial mission. So you might be saying, "Jay, this is cool, but why is it even remotely hard to fly helicopters on Mars?" I'm seeing drones all the time on Earth. So the main challenge is by far the fact that there's basically barely any atmosphere, about like 1% of the atmospheric density that you have on Earth. So like for comparison, that's about flying at like 100,000 feet, so like three times Everest. And so while the atmosphere is very little dense, so it's hard to generate lift, there's still a lot of gravity. Like it still has 1/3 of the Earth's gravity. So there's still a lot of basically force trying to pull you down while it's hard to generate force to go up. Um, Beyond the aerodynamics challenge, it's also a world that's very far away. It's about 180 million miles on average. That means it takes 80-minute communication one way, 30 minutes the other way, and that delays grows and shrinks as the distances to Mars basically varies during the year. And interestingly, it's also a very cold world. So we went as low as minus 90 C during the Martian winter. Uh, so the vehicle that we designed to handle that was so small coax watercraft. So we say basically coax because they're like two pairs of opposite of carbon fiber blades, which are rotating in opposite directions to cancel each other's torque. The whole thing was about 4 pounds. Tip to tip, it was about 4 feet, 1.2 meters. And it was originally designed just to do like flights up to 5 meter or 15 meter high, 15 feet high, sorry, 300 meters long and 90-second duration. That's what we had designed this to do. Uh, if you're operating drones on Earth, you're probably familiar with like charging drones, like, you go in there and you swap the batteries. Of course, we couldn't go there to do that. So it's got a little solar array that you can see on top, which enables it basically to recharge its own batteries. The batteries themselves, you might be used to hearing that, that NASA missions are they own custom-made computers and avionics and everything. But here, all the batteries and the processors and the sensors were all commercial off the shelf. That was the first time we were doing this for a NASA mission. The reason we were allowed to do it was because it was the technology demonstration, so the lowest class of NASA mission that you can think of. So we were allowed to take risk to potentially get a high reward. Uh, but we learned a lot of lessons from this, which I'm going to go over in a minute. If you look at it from the inside, you can see that the six batteries are like the orange cylinders that you can see on the inside. We store them this way because actually the battery material enables us, like the electrolytes actually has a lot of like thermal inertias. So we actually leverage that in the thermal design of the system. And we got the avionic boards around and the sensors on the bottom. So here you can see basically the laser altimeter and the camera is just the one thing over here. So that's how we get delivered to the surface. We arrive with the rover. We were attached with the belly of the rover. That's a picture right after deployment. And we were lucky that there was a spot compatible with our flight because we had at first assumed that we wanted to fly over a terrain that's fairly flat and level. Like the goal was not to pull a performance in autonomy, just to show that flying was possible and there was a terrain available right there. Actually, you can see the spot where we landed right here. If you can see the orange residuals right there, that corresponds to the fuel residuals from the landing system. And this was the image, this was the video of the first flight of the rover. So the first flight of the helicopter that was shot from the rover about 60 meters or 200 feet away. That's about as close as they wanted to get because they were convinced we were just going to crash and burn and damage their pressure sense instruments. And the first flight, as you can see, was fairly simple. It's just go 3 meters, hover, do a turn in place, and go down. Because that was literally the only job we needed to do, just show that that one thing is possible. There was no reason to like try to be fancy, go places on the very first flight. So, but with the first flight done, we got the chance to complete the 1 month mission and like show that we could do much more than just do like a flight on Mars with no science on board. We also had a high resolution camera. And even though we had no instruments on board the helicopter, this high resolution camera provided super valuable to basically scout the terrain ahead of the hover. You can actually see the hover is right there. And it was able to provide, like normally when the scientists basically on like for the instruments on the rover plan their drive, they just like use a telescope that's on the rover and they try to look at places which are 100 to 200 meters away and try to see like if it's worth planning the next day of driving to go to. It's extremely hard to do because you have like a poor perspective. So being able to send the helicopter, get basically a bird's eye view with like a few centimeters per pixel, many times basically give them the insight that, hey, this place looked interesting from the telescope on the rover. We sent the helicopter, turned out it wasn't as good as we thought. And so they saved basically days of driving to, instead of going to the poor location, go to the location. So that went to show that like even if we didn't have a proper science payload on this, we still contributed science return to the mission. And the proof of it was that we basically got extended, to NASA at first, helicopter was a cost because like they needed to dedicate bandwidth in the telemetry and operation time to operate the helicopter, which was at first not assumed to be doing science. But when they realized that we could actually contribute to the science return by scouting ahead of the hover, we were allowed to basically keep going as long as we could. And that lasted for 3 years for us. These are some of the cool images, which shows the kind of vantage points that we can get with the helicopter. This kind of terrain you couldn't even imagine thinking going with the hover. You got slope over 30 degrees. The hover basically was limited to going on these slopes here. It could never even approach some of these rock outcrops that we have. So overall, we lasted for almost 3 years, 35 months, did 72 flights instead of 5, flew 17 kilometers instead of just 150 meters. And we demonstrated the benefits of scouting, with a helicopter in front of the rover. We found some sample site for the Mars Sample Return mission, which was a big hit at the time, and basically showed like the advantage of this new platform for planetary exploration. We One of the big surprise was that we were able to survive the Martian winter. That was the one thing that, if you would ask the team at the beginning, like what would be the ultimate physical limit of the system, that would have been the thermal. We look at it in a minute, but we found that this off-the-shelf avionics basically a lot more robustness that we thought, even to the NASA standards. We eventually ended up damaging the rotor. That's in January 2024. I think I might have a picture right there in my. So we flew over a terrain which had basically no texture. You can see like the sand here. Like normally we're like using rocks to basically to do feature tracking because there is no GPS on Mars. And when we flew over the dunes, basically we had not adjusted like you know like we were basically pushing it too hard. We did not find texture, and basically one of our legs basically hit the top of a dune, we think, and just the centrifugal forces from that hit basically damaged the blade. We don't think it was a blade strike, but only the energy from the leg hitting the dune broke the blade. And so we've been sitting on the ground since, but Ingenuity is still active. It's actually still collecting atmospheric data from the ground. And if the rover comes back near Ingenuity so that we have an opportunity to download the data, we should have about 2 to 3 years of atmospheric science, which would be downloaded back to Earth, even though it's not flying. Uh, so quickly, that's a short video that puts to scale the difference basically. So this is the area we are initially planning to fly in. And then you saw like just how much further we were able to go with this helicopter. And I'll say that as you're going to see like the scale grow and it looks impressive compared to where we were, the actual main limitation of like how far we were able to go was actually the rover. A lot of time we had to wait for the rover because we only had a communication system designed to talk with the rover, and we didn't have direct to orbit. But I think you can appreciate basically that this is essentially a system that enables us to now do planetary science at the scale of a region, while maintaining resolutions that you would have with a rover. So we're very much seeing that as a platform in between the big rover laboratories that are good to be up close, but are struggling to basically rove long distances, and the orbiters which have global coverage but poor spatial and temporal resolution. So with that said, let's get into the interesting stuff, which is what were the key enablers behind it, and also why do we keep pushing on this? So I was just mentioning that our vision now is to go into constructing a science helicopter, which is called Mars Chopper. That's the concept that we're promoting right now. It's a much bigger platform, so 6 rotors. For scale, each of the rotors is about the same size as Ingenuity. So that means tip to tip, this one is about 12 feet wide. So it's a much bigger platform. It can carry up to 10 pounds, 5 kilograms of payloads. And we currently have a mission concept to go to Valles Marineris, which is the largest canyon in the solar system, because it is at the scale of a region. It's one of these places where a rover would not be able to go through the various geological layers, but the helicopter can fly back and forth and explore basically literally that trench through the history of Mars. So I thought it would be interesting, to basically map, the technology that's already available, and that made it possible to fly a mission in that remote cold world, and the technology that we've been developing at JPL since 2018, which was the end of the R&D for us for Ingenuity, and what we think is enabling for the future science missions to Mars. And I think some of it will be relevant to concept that we can think for the Biosphere. So some of the challenges basically for that Ingenuity was facing was, okay, we didn't have any GPS, so we needed to have vision-based navigation to be able to do any autonomous operations. There was no operator nearby to swap the batteries, so we needed to have a solar array to be able to recharge. And and once a day we could recharge. Most of the energy was actually spent to survive the night. Because the overnight temperatures went down as low as -90 C. And so we had a lot of basically we did a lot of work to optimize the thermal budgets. Like how when we spend our energy, like do we like you need to fly not too early in the morning, um, so that basically the you have the right conditions to fly, but you also not to fly too late in the day, so you can basically charge your battery when there is sunlight to be able to survive the night. There is no operator nearby to download the data, so we needed to have that communication link using the rover, then going to an orbiter, and then going to Earth. Um, so that was for Ingenuity. Now for the next mission, like we want to send like we think that Ingenuity has done such great work that JPL is basically trying to propose a helicopter-only science mission, which is going to be something like Chopper, but it's only going to be a helicopter. It's not only going to be too expensive to send a helicopter and a rover, but also like we want have the space inside the entry capsule to basically to fit both. So it's just going to be the helicopter. So we need to be able to like do like 3 kilometer long traverses. That's the only way that we're going to be able to cover the length of that canyon. So we need to have like uh, much more advanced vision-based navigation, not just visual odometry, but also like map-based localization, so that we can basically like refine our trajectory and target like very tiny spots from kilometers away. We need to be able to have like landing site assessments and make sure that we don't only we land on locations which are safe. And for Ingenuity, we were just like targeting safe spots. Now we want to have like onboard slope and hazard detection, multi-day autonomy. So we don't want to have basically someone on the ground to plan the next day, which is what we're doing for Ingenuity. We'd like to be able to send a command and have the vehicle be on its own for like a week at a time or more. And because it's a helicopter-only mission, we need to basically deploy it without a lander. We could try to fit a lander, but just like for the rover, that would just take so much space in the entry capsule that we'd end up sacrificing the size of the rotor, which directly translates into less payload. So we need to have media delivery. We need to have direct-to-orbit communication because there is no rover. So now let's look into where we are now. So just for Ingenuity and for just like for the future helicopters, like our sensors are like off the shelf. It worked for Ingenuity, it proved reliable. So we're gonna bank on it even for the Discovery mission. We had no fatal radiation events despite everything being off the shelf. We had a Qualcomm navigation board, and everything went well. For the science mission, we're going to have redundancy, because it's going to be a higher class mission. So we need to have more more robustness, but we're not going to go into complex space-related computers. So earlier I was talking that we were working with GPS denied navigation. So that's what that's what it looks like in practice. So we're using feature tracking on the camera, which is like the eye of the helicopter. And basically from these features, we're able to estimate the displacement of the helicopter, and that's what we use as feedback for the autopilot. So it's like our visual GPS, if you will. The one we had on Ingenuity was fairly basic. It was assuming that the ground was flat and level, which worked very well at the beginning when the world was indeed flat and level. We had very low, this is the drift. So basically the amount of error as a percent of the distance traveled. So state of the art, basically you want to be about 2% or less. And we could see that even with this simple system, we were hitting this. But as soon as we started to go into the extended mission, when the world was just more complex, we would see flyover slopes and complex rocket crops, we see that the performance of the vision-based navigation started to degrade, which means that in practice, when the scientists would say go to this location, they had to make sure that they were targeting a place which was free of hazards based on assessment from the orbital images on a wide enough scale that you basically were guaranteed that Ingenuity would not land on a hazard. So we need to change that. And so now we designed basically a new approach that's basically it's able to do range visual inertial odometry, without making any 3D assumption about the world. So if you're familiar with robotics research, you might hear that visual inertial odometry has been able to do that for a while. But being able to integrate the rangefinder, the altimeter in there, well, actually almost no one is doing this. And it's actually surprising because the simplest trajectory, for a helicopter is to fly from A to B with a uniform velocity. And when you do that, that means there is no excitation on your accelerometers, which is the only thing that can provide metric scale. So basically, if you fly the regular VIO without an altimeter, you're going to see a huge drift in the scale of the scene, which can be up to 8 to 10% of the distance travel. Um, so being able to achieve that like over a 3D world was like one of the like first thing that we did back in 2020. And now we've put a lot of mileage on it. This has been tested in the field and in simulation, and that we think that's what we're going to fly for the next mission. One thing we added was also hazard detection at the landing sites. I was mentioning that the scientists used to pick up basically the landing spot. Now we basically have like we're using structure for motion to detect slopes, rocks, like anything that could be a hazard on Mars. So the helicopter is able to basically target footprint, which is like just as wide as its own footprint, just with like 50% margin, and land accurately in it. We're also doing vision-based navigation, so we're able like to completely eliminate the drift, and the scientists can show like a spot on the map, and we're going to be able to land within a few pixels of it. We've already demonstrated that during the landing of Mars 2020, that was done to like target a spot in the J0 crater. But now we've implemented it and tested it on board Qualcomm boards, which have been flown in field tests with our helicopters on Earth. Um, Lastly, moving away from like visual autonomy, I wanted to talk about the power subsystem. Um, and that's really one of the things that I think is not done often with drones on Earth. It's just the idea of like put a solar array on your drone, basically make it completely autonomous. Like you don't need to go and swap your battery. And Ingenuity was using mostly commercial off-the-shelf components for this. We had like six LiPo batteries, unregulated battery bus on the system, solar cells, which are also off the shelf, but just like optimized for the mass spectrum. And then we had like two like simple boards to basically to have the interface the charging with the rover and manage the power of the helicopter on two regulated power outputs. And thermal survival, I think probably one of the biggest lessons learned of Ingenuity was so here you can see basically the state of charge at the end of each sol or each day on Mars. And you can see that when we landed in the spring and going into the summer, like our thermal calculations were right. We were always finishing basically the day with like 100% state of charge. But as we went into the Martian winter, so it takes the year takes twice as long on Mars as it did on Earth. So that's why you see like the offset here, but that's the Martian winter. And you can see that we stopped hitting 100% because we didn't even think it would survive, to be honest. And initially, it stopped working because we had the thermostat set to minus 15 Celsius, and we thought this was the end of the mission. Like, one day Ingenuity like did not communicate with the rover. We knew it was a cold night, and we had honestly prepared like the press statement for NASA to announce the end of mission. And then last resort, basically the team tried. Let's just try to see like if we could set if we could try to like send a single command to the helicopter during the brightest part of the day when there's the most chance that it might be alive, and just see like if we can get in contact with it. Just try to set the thermostat to like minus 25 C, but instead of like minus 15. So basically, we're telling him it's okay to freeze for the night. Like we don't want you to try to stay warm tonight, and we think it might work. Um, and it did. So in practice, like Ingenuity was able to survive the winter and eventually go back to 100% state of charge at the next summer by literally letting the electronic freeze overnight. And that was something that we thought would be impossible with like off the shelf, like cheap avionics and electronics. And to our surprise, it did work. So if I have one message today is there's a lot that you can do with like non-space rated avionics on this platform. Like it's not just for the big NASA missions. It's something that like you could consider even for R&D projects on Earth. Okay, I'm running short on time, so I'm going to go now to okay, why does it matter? So we're trying to propose this concept here, which is called Sierra. That's called for like snow and ice exploration using remote sensing, quantum and autonomy. We have a lot of people involved. Seth is one of the people here at UMaine. We also have Brent Minshew at Caltech, HP Marshall at Boise, Jennifer Jacob at New Hampshire. We have people from industry. We've got people from the Army, Tony Fragoso and Sheldon Hill at Corel. And the idea is basically like, can we adapt this science helicopter concept from Mars to Earth? And the idea behind it is that since we we already have a platform that has demonstrated, that we could do interesting things, very far away from Earth, like down to -90 C, and at that density altitude that are much lower than what that we would find here on Earth. Like, are there low-hanging fruits that basically could apply to cryosphere science? Uh, and so far we are we are receiving interest. So these are just like some of the few examples. So for instance, HP Marshall is looking at snow on the West Coast, like trying to measure snow water equivalence. The Army is also measuring snow water equivalence about the same in the same radar wavelengths to assess traversability for ground vehicles. Uh, and these people are already flying radars on drones. So this is like one radar which was developed by Andrew and Tang at JPL and is flown by HP every winter in Boise. It's about a foot wide and it's flown on this helicopter, which is about the same size as Ingenuity. And for them, basically, this has become the state of the art. They're using that to get higher resolution measurements, to get ground validation for things like NISA. The bottleneck is that they need to send a crew on the ground. To do that, they're they need like a 3 to 4 days heads up, preparation before a storm event to be able to do this. And when they do it, they're limited to like where the pilot can access, the closest access road and the line of sight it can have from it. So the bottleneck has really become the logistics. Um, Brent is using would like to fly similar drones in Antarctica to assess the formation of cracks and the dynamics of the grounding zone. So it seems that the general idea of flying sensors close to the ground to basically fill the gaps that you have with classical satellite and airborne data, whether it's ground validation, spatial resolution, temporal resolution, seems to be getting traction. And this is what Sierra is. So in a nutshell, we want to propose a platform that can uh, traverse for hundreds of kilometers, to access the relevant site. We can also drop it from an airplane, like the same way we do entry, descent, and landing on Mars, like this is thing that we are used to doing. And then once it's there, basically, you can fly close to the ground about 10 to 15 kilometers a day. But the point is not the maximum range that you can get because you're using a rotorcraft. Otherwise, you would use fixed wings. It's more like, can we target segments that are driving the uncertainty of your models? So basically, we stay there, and basically we have one or multiple helicopters which might be carrying different payloads, so you can get basically different kind of data. And you do daily or hourly passes in these conditions. And the drones can stay there for a whole season. They just survive, recharge during the rest of the day. They survive every night. Um, we think that a lot of this technology, from the visual autonomy standpoint, from the power recharging, there's a lot of low-hanging fruits. The things which are new, on the Earth system, but none of it is a bottleneck, is the fact that okay, there is a denser atmosphere here. So in the thermal equations, we're going to have to deal with connectivity, which is something we didn't have on Mars. So we're probably not going to be able to do as cold or not for the same budget. But it's okay because we also have a denser atmosphere to carry more batteries. And also, one of the questions how do we deal with icing and storm survival? If ultimately you want to be able to survive a whole season, we're going to be able to do that. But you can already get a lot of data, without having to survive storms. For instance, here in the Sierras in California, you barely have it's 2 or 3 storms a season. So we think it's promising. We're trying to to get funding to start this research. There are challenges, it's not just low-hanging fruits. There are things which are very specific to Earth. But so far, we don't think any bottleneck. So we're hoping that there's going to be a lot of interesting technical challenges and hopefully a lot of opportunities for new measurements for your community as well. And finally, I'll just finish by saying that, in one I've been, one of the things I've been in touch with Seth was, to take this Sierra concept, see how, we can test it at JERP. We think it's a fantastic test site to be able to VNV this technology and the science in relevant environments, so that ultimately we can get deployments in all the relevant data on Earth. But what I also think we're going to get is a lot of technology spin-off and information for other NASA missions. For instance, if we end up doing that multi-day traverses at JERP, that's something that we have never done on Mars so far. So that would be a VNV test that this is ready to go for the next mission. Also, beyond Mars, like, we've been going to Mars for like 40 years. The one of NASA's goal is to look for extraterrestrial life, and it's the focus is likely to shift to ocean worlds, like, so the moons of Jupiter and Saturn, like Enceladus, Titan, Europa, in the next 10 to 20 years. And from a robotic standpoint, we know close to nothing about mobility in these environments. Like, we talk about vision-based navigation on sand, like, but how does it change? Like, when you're like when you're flying over powder, when you're flying over ice, which might have specular reflections. Like, so these are all the aspects that we need to start facing right now if we want to basically develop send these missions to this ocean icy world in the next 20 years. And we think that Europe could be also a fantastic test site for all of this. And with that, I'm sorry I didn't start at 12, but I did just 30 minutes. So hopefully that works out. Thank you.
Thanks, Jeff. Questions for Jeff? Nestor?
Hi, Jeff. Thank you. I was wondering, what are the capabilities we saw yesterday about the cryobots able to drop small probes into the ice? And I was wondering, what are the capabilities for a helicopter like this to carry a small payload that it will have to, I guess, activate? So it's actually manipulating small objects versus just carrying sensors.
Really to do like manipulations while flying or on the ground?
On the ground.
Oh, on the ground, I think there's a lot of opportunities. So actually, when Mars sample return was still a thing, you can look at the sample recovery helicopter concept. So we were actually like planning to use the Ingenuity platform to go fetch samples on the ground. I'm trying to find it as an actual picture. Um, but that may be the closest concept. Like, but there is like, I can show you at the seminar that we have in April. Like, we basically built a prototype of this guy, which basically, so it was basically the Ingenuity format, so it can fly up to a kilometer. Then it lands. When it's landed, it's got like no small wheels and would like basically finish the job, like go to the test to a like the manipulation site. For us, it was like to pick up samples, and it would have like this small robotic arm to go pick it up. The whole sampling mechanism here was 250 grams, like this whole robotic arm here. And that was like, just like within the limitation of using the Ingenuity platform, which was not developed to have a payload and flying on Mars. Like, on Earth, you have a lot more margin, like, to put bigger robotic arms, or like, to have more complex mechanism. We currently estimate that, like, on if we wanted to fly up to like 6,000 meter elevation, we could carry a 10 kilogram payload and still have a 10 kilometer range, with like without doing any work, or like, on motor developments or like, going fancy on none-off-the-shelf components. Hopefully it answers your question. But let me know.
Yeah, very cool.
Jeff, in the theme of the workshop, I mean, the things that are floating through my head that it'd be nice to just have people think of, this is more a comment, but I'm thinking about this type of a platform for doing, autonomous repeat surveys over, your 100 kilometers with LiDAR to capture surface elevation change as a result of surface melt and, winter snow accumulation. Doing repeat surveys over land surfaces that are unstable, kind of capture a time series of instability through the season where it's really hard to, it's super expensive to get an airborne flight covering Juneau ice field. You're talking $30,000. If you had something like this, you could fly over and over and kind of went from a hub to kind of capture that data. And then I also think about some of the work that John talked about yesterday about telemetering data back. When you have these larger data sets, these could potentially be fairly large data sets. So how are we thinking about that? So I'm trying to think about how we might kind of coalesce a lot of these ideas together for the white paper. So that's more of a comment than a question, I guess.
Yeah, no, happy to help brainstorm it and like, talk about it further. But yeah, and especially at Europe, like, the fact that, like, you have like this like access to power at the base, like, like we can do a lot of things without having to go even solar at first. Like, we can, I think, like we discussed, like, CES, we can put a charging dock basically there, like, so the one can go back every night. Like, so we could do this like repeat, like, basically very easily, like, probably like within a year of development with a regular budget, because like you guys are, like, I think there's a benefit of Jerp, like, being able to have this test site without having to go extremely remote and do that.
Well, for sake of time, we should probably roll on to the next.
Yeah, thanks,
I
Jeff.
think we have one more talk this morning.
One more this
Yeah,
morning.
Great, thanks.
Thanks for having me.